Okay, this video is going to finish up some remaining sections of Chapter 4, and I'm also going to point out a few concepts that were consistently missed in the midterm exam. By the way, the midterm exam spread is A's, B's, C's, and a little bit lower also. So I do curve at the end of the semester, but I think also that was a difficult midterm exam. So I would also like to go over the last problem with the missed, find the four problems with the program. There are actually five serious problems in that program, but I wanted you to find 4 of them. So I'm going to go over a concept that was pretty consistently missed in there, which is part of Chapter 4. So so let me skip down. We did a lot of parts of Chapter 4 already, but there is a part that's related to the concept that everybody missed. A lot of people missed, not everybody. And I want to go back over it. And that's this slide. So, definitionally, first I'm going to point out a few things. Where's my pen? There it is. This right here, this is a function, right? We have a function. These variables of the function are called parameters. So x and y are parameters. So this is actually a very important concept. The parameters only have value or only have meaning in the function. Outside of the function, x and y don't have any values. And outside the function, they don't exist. So when you call the function, like up here, here's part of the main program, and it's going to call the function. The function is called average, so it calls average, and it puts arguments. These things are called arguments right here. Value 1 and value 2 are the arguments, and they're part of the main they're part of the main program, and the function is being called. So the parameter, x and y is a parameter. The parameter is the variable which is part of the function's signature. So remember, this is the function's header or signature. And so the variables that are a part of that header or signature are called parameters. The argument right here is the expression that is used when calling this function. So the arguments are the things that are passed to the function for the function to do something with when you call the function. So notice, like the exam problem, I call the function average, and the arguments are value 1 and value 2. In your exam they were a and b, but the function, the definition of the function, uses variables x and y, which are parameters. So x will take on the value 1, y will take on value 2, and the function will get evaluated, and whatever needs to be returned will be returned. So x and y only exist also inside this function. That was missed quite a bit in the midterm exam. So remember, these are arguments up here when you call the function. Arguments are when you call the function. Parameters are in the function definition. So they're all kind of forms of variables, but the definition is different. So okay, so I wanted to point that out because quite a few people missed that concept. So let's go on to the next part, the optional sections of Chapter 4, which I'm not going to be able to cover all of it. There are a lot of examples of different numerical techniques, but this is a programming class, so I'm going to pick some numerical techniques from time to time that are useful for engineers, or also kind of universal programming concepts. So one of those universal programming concepts is a concept of recursion. So that we will use recursion to compute factorials in a Fibonacci sequence. Recursion is a function that calls itself or invokes itself. So you call the function, your main program calls the function, but the function keeps calling itself and then finally gives you an answer. But a function could actually do this indefinitely if you set up your function that way. but there are system limitations. Like if you keep calling yourself until you get to a 0, for example, there's only so many bits you can use to represent 0 in your given system. So like I said, I'm going to use a factorial computation and option. So let's talk about factorial first. Factorial is useful in statistics quite a bit. So if you want to find probabilities of something, many times the formula involves factorials. Also, factorial is used in a lot of infinite series. If you are taking calculus or trig, you should be introduced to infinite series. So what does factorial do? So for example, the number 5 factorial is 5 times 4 times 3 times 2 times 1. So that's what 5 factorial is. There I've defined it symbolically. So n factorial is n times n minus 1 times n minus 2 times n minus 3. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1, and that happens to equal 120. 5 factorial also equals 5 times 4 factorial, correct? Because there's 4 factorial right there, and 5 times 4 factorial. Similarly, 4 factorial equals 4 times, times 3 factorial, correct? So we will use that fact when we develop a function that will compute factorial. So here's a function that computes factorial using a loop. It's an interesting function. I think it's good to sit and look at it carefully and understand what it's doing. So let's look at it carefully. So the first thing is that factorial numbers can oftentimes be very large numbers. So it's good to declare the computation of factorial to be of type long. That is because the numbers can get very big, and long allows you to use more bytes to represent your number than does double. Okay. So this part is just declare some variables. J is going to be just a loop iterator, and term is going to be the answer. So the first thing I have to going into this function, this is just a function that a main can call, is that if I ask for it to compute 1 factorial, well, 1 factorial is just 1. So I say basically right here the answer is 1 if the user passed in 1 to the function. So user calls the function factorial 1, the answer will be 1. So I will just return 1. But if the user passed in a number other than 1, if k is, let's say, 5, for example, then we will start doing a loop. And what happens is you go into the loop, says j equals 2. If j is less than k, now remember in my example k is 5, I'm going to pass in 5, and it's set j equal to 2. If j is less than 5, which it is, then I'm going to say the ending number is 2. In the first pass through there. It's actually term right now is 1, so term gets 2 times 1. So great, that's good. Now I go through the loop again, I increment j. J is now 3. J is still less than 5. So term, which is right now 2, gets multiplied by 3, and so 2 times 3 is 6. But j is incremented now, it's still less than k. This is worthwhile for me to write this down, I think, as we go through. So initially, seeing what happens here, initially term is 1, especially if you make k call the factorial function with k equals 1, that's what you'll return. Okay, so term is 1. K that I pass in here is 5. So, and then we have the iterations through the loop, which is j. So initially, go through the loop, j is 2. So j is 2, it's less than k equals 5, and the answer will be 2 times 1, which will be 2. Next, I iterate j. J is now 3. So term gets 3 times 2, which is 6. I'm still less than 5, so I continue doing the loop. J is incremented, so it is now 4. So term gets 4 times, gets multiplied times 4, so 6 times 4 is 24. Increment j. J is now 5. Term gets multiplied, the current value of term gets multiplied by 5, so 5 times 24 is 120, and now j equals k, and I exit and give the answer out. So I actually did this program, but I modified it a little bit so you could see what was happening. So here is the program shown, and what I did was put an extra print statement in the loop, so every time I go through the for loop I can see what the value of term was. In my example here on the slide, I computed the value of 1, 2, 6, 24, and then the answer spits out as 120. So when I run the program, enter a positive number 5. Oh, I have a get character. Oh, I got an extra get character in there. But yes, it goes 2, 6, 24, 120. Oh, that's the rest of the program. So 5 factorial is 120, computed non-recursively, which is by a loop, which we're doing right now, and recursively will also compute to be the same thing. Okay, so it's worthwhile to step through this loop and understand what's happening with it. So let's look at a function that does it recursively. This is the recursive one. Hard to show step by step, but let me tell you what's happening in it. So recursively, I enter the loop. If the user asks for 0, just return a 1. So 0 factorial must also be 1. Else, you're going to return the user's number times, maybe the user is 5, times factorial of 4. And how do you compute the factorial of 4 is to go back and recall the function, which will say factorial of 3, which will say factorial of 2, or factorial of 1. So sit and think about what's happening here. If the user says compute 5 factorial, it's going to be 5 times compute 4 factorial, which will be it will be in a loop until it's done. So interesting little recursion that occurs. So the loop calls itself until it's done, until k gets to 0. Okay, so Fibonacci numbers. Here they are, 1, 2, this is a Fibonacci sequence, 1, 1, 2, 3, 8, 13, 21, 20. This is how it works. You take the first two numbers, 1 plus 1 equals 2. Then you say 1 plus 2 equals 3. Then you say 2 plus 3, which equals 5. 3 plus 5 equals 8. 5 plus 8 equals 13. 8 plus 13 equals 21, etc. So this Fibonacci numbers are used a lot in biological sciences, and I am going to actually say less in engineering. I haven't seen them so much in engineering. So here is kind of a cute picture, I think, the Fibonacci spiral. What you do is the area of each one of these squares is the area relates to the Fibonacci numbers. So in this case, this is area 34, this is 21, this is 13, this is 8, 5, 2, there's 1, 1 in the middle. So so you keep doing these squares and you get this spiral. So apparently this spiral exists in, for example, seashells. So let's go on. Okay, now I'm going to show you a function that computes the kth element, or the kth number in a Fibonacci sequence. I want to return the, let's say, the 7th number in the sequence. And this is a function that will find the 7th number in the sequence, and it will do it using loops. So this loop was actually kind of hard to understand, and I ended up putting some printf statements in it so I could understand what it was doing. So let me show you a little bit what it's doing, and then I'll show you where I put the printf statements in, and then I'll show you how it runs through each loop. So it basically says, let's say the user wants to find the 5th number in the sequence, for example. So you enter the function. You start with your final answer being 1. The terminal answer term equals 1. And then it says if the user number is greater than 1, then we're going to do some loop stuff. So user entered 5, let's say, in this case. And then it will initialize, before I go into this for loop, I'm going to say my previous 1 number and my previous number 2 behind are both equal to 1. So it's really saying, for example, if the user asked for the 3rd number in the sequence, or the 2nd number of the sequence, it says the previous numbers are all 1. So the 2nd number in the sequence will still be a 1. And then if the user asks for the 3rd number in the sequence, then we start going through this loop. So let me show you what happens. Final answer gets the sum of the previous 2 numbers, which I showed you that in the sequence to begin with. But then there's some other things going on here that are maybe a little difficult to understand. So what I did, to make sure I could understand what the loop was doing, was put some printf statements in it. So I've added, as I enter the loop, I'm going just to print out the value of n, which is my loop iterator, previous 1, previous 2, and terminal number. And then my loop happens. Final answer, terminal number, gets some of the previous 2 numbers. Then it says previous 2 gets previous 1, and previous 1 gets the current value of the final answer. And then I'm going to go ahead and print out what these values are right now, and I'm going to put a get character in so I can pause each pass of the loop and look at the answer and run that program, because I want to figure out how this function is computing the kth number that the user asks for using a loop. So here's what the output would be. Now I took off my print statements, but remember I have a print statement right at the beginning of going through the for loop, and then right at the end of going through the for loop. So in this case, my user said, what's the 7th number in the sequence? So 7 is greater than 1, so that means we're going to do this loop, and I initialize previous 1, previous 2, and term with the value of 1. Then I do what the loop says to do, and it says that the terminal value gets previous 1 plus previous 2. So this plus this gets that, and that is true. 1 plus 1 equals 2. And then it says that the new value of previous 1 will be the value of term. So it is true. So then I increment my loop, and the n is now 3. This first row here just reflects the end of the loop, previous loop. So I re-enter the loop, but the values haven't changed. I do what the loop tells me to do. So the terminal value gets 2 plus 1, which is now 3. The new previous 1 is 3, getting ready for the next iteration of the loop. And we go through and each pass of the loop. So you can see 8 equals 5 plus 3. That's every time that I add up term equals previous 1 plus previous 2, term equals previous 1 plus previous 2, and it goes through the loop. So it's interesting, this loop is interesting, how values get updated with these lines, as well as computing the final answer, which is the sum of the previous two numbers going through the loop. I think the loop is interesting. I think it's worth understanding. Now, the recursion example of this was very difficult to understand. Even when I printed out each pass through the loop, it's kind of crazy, and it's actually more computationally intense than computing it using a loop structure. So my takeaway from that is, although I could solve this problem recursively, it is not the best use of my CPU time. If I was doing some massive big computation, I would care about such things and being efficient. So it turns out that the loop approach is much more efficient than the recursion approach for the Fibonacci sequence, not so for the factorial. So right algorithm for the right problem is the bottom line. If you would like to look at the recursion for this, it is in your textbook, and you can also Google it and see, but it is kind of an advanced programming concept that involves doing some diagrams to show how the program is functioning. So I'm not going to ask you to learn it. So this is the end of what we are covering in chapter 4. We will now move on to chapter 5.